Hello, calculus scholars. We're going to be doing skill 35 today, which is Riemann sums and trapezoidal sums from equations. So what that means is that we are not going to be providing you from a graph, and I'm just going to kind of work on these delta math examples themselves because we are going to want to really take advantage of the calculator feature. All right, so what they are going to always give you, I'm going to kind of circle some important information here. The first thing is 4 subintervals of equal length are used, and we are using a right Riemann sum as well. So I like to kind of circle those terms. So what I'm going to do first is I'm actually going to do the interval width. And the width is going to be 5 minus 3. And we can always find that by looking at the top and the bottom number of the integral over 4. So that's going to be 2 over 4. So we're going to be going every 1/2. And what we're going to want to do is we're going to want to find the right Riemann sum approximation for the integral. So when we're kind of working this out here, I'm actually just going to write this in integral notation. And our first rectangle is going to have a width of 1/2. And the height of it will be f of 5. So we're just going to start from the right. And then the next one is 1/2 f of 4.5. And then we have 1/2 f of 4. And then we have 1/2 f of 3.5. Now, if you want a shortcut for these rectangular approximations, what you can actually do, since all of them have, 1/2, you can actually just take out the 1/2 and just add, f of 5 plus f of 4.5 plus f of 4 plus f of 3.5. And I even like to, just convert this from f notation into the function itself. So we'll have 5 over 5 plus 5 over 4.5 plus 5 over 4 plus 5 over 3.5. And we can actually now go to our calculator. So in fact, I want you to use the Delta Math calculator and take advantage of it. So I'm going to enter it in. So I'm going to have 1/2, and then I'm going to put in parentheses, I have 5 over 5 plus 5 over 4.5 plus 5 over 4 plus 5 over 3.5. And we get 2.3948. So it says round to the nearest thousandth, so that means 3 decimal places. So we're looking at about 2.395. And let's see how this works. And it works beautifully. So what I will say, I always like getting used to looking at the integral notation and getting used to that. I even like the first setup usually as well. So if it is right, start at the top limit. And if it is left, you're going to start at the bottom limit. And it's a little bit more interesting when we actually start in the middle. I will say that you could get from, if you kind of get this 1/2 shortcut, you know, pulling it out, this is particularly useful on those right and left and midpoint rectangle sums. So they're particularly useful. So some people just like to immediately take out that width. But I always recommend, you know, just finding the width right at the beginning. All right, let's look at another one. And I think it's just good to kind of keep on doing these and getting the patterns of them. They actually do give you, you know, different types of functions as well. So this one is a midpoint one, and I'm glad that we have a midpoint one. So we're going to have 6 subintervals of equal length, and we're using the midpoint Riemann sum. So like before, I always like to be thinking about my width. So my width is 2.5 minus 1. And we have 6 intervals. So you always put the number of intervals on, or subintervals on the bottom. So this is 1.5 over 6. So this is equal to 1/4. And it may actually kind of help you to kind of draw a number line from the midpoint. You know, this gets a little bit trickier. So I'm going from like 1 to, you know, 2.5. And your intervals are going to be like 1.25, 1.5, 1.75, 2, and 2.25. Now, halfway in between is 1.125. This would be 1.375, and so on. So I always just kind of recommend, you know, kind of mapping out your intervals and then starting with the midpoints each time. So when we're doing this Riemann sum, so I'm just going to write the integral from 1 to 2.5 of 3 to the x dx. We know that our width is 0.25. And just to save us a little time, I'm just going to use function notation. So we're going to have 1.125 plus, and we're just going to go up 0.25 each time. So we're going to have f of 1.125 plus f of 1.375 plus f of 1.625 plus f of 1.875 plus f of 2.125 plus f of 2.375. So I always like to kind of start, you know, think about that first interval, you know, what's the midpoint of that first interval, and just keep on adding the width to those x values. And if we want to actually see what this looks like, in terms of our equation, this is going to be 0.25 times 3 to the 1.125 plus 3 to the 1.375 plus 3 to the 1.625 plus 3 to the 1.875 plus 3 to the 2.175 or 25 plus 3 to the 2.375. So we're just going to use the handy dandy calculator and let it actually compute its Riemann sums. So let's see, our width is 0.25. And our, we're going to do 3. And if you want the exponent, you just do the A to the B button. So you're going to do 3 to the 1.125 plus 3 to the, or you could do the caret key as well. (1.625) plus 3 to the 1.875 plus 3 to the 2.125 plus 3 to the 2.375. And that is a midpoint Riemann sum. So it says to the nearest 1,000th. So we're looking at about 11.423. And we are looking good on that. So it's a little tedious with the numbers there on that one. So that kind of makes it a little bit more interesting. Good. The last one that we're going to do is a trapezoidal sum. One thing that is nice about this one is it's only 3 subintervals, so that is going to make your life a little bit easier. Because the last one we had 6, which was quite a bit. Our limits of integration are 0 to 1.5. That gives us our highest and lowest x values, and it's equal length, and we want a trapezoidal sum. Okay, so like before, I like to always find, what my width is. So I'm going to do 1.5 minus 0 over 3. So my width is 0.5. And if I'm going to be mapping out my trapezoids, I'm just going to kind of do the trapezoid area formula. And I even like to write down what that formula is. And note here that h is actually our width because they are trapezoids on their sides. And if I'm actually computing this, so I'm just going to take one trapezoid at a time. So my first width is, I'm just going to do the 1/2. And I'm going to do f of 0 plus f of 0.5. And the width is going to be 0.5. And I think it's even helpful to just kind of like, since they're kind of a little bit busy, even just line them up, column wise. I think it's easier for some people to kind of see them like that. All right, and then the second trapezoid is going to be f of 0.5 plus f of 1 times 0.5. And then the third trapezoid is going to be f of 1 plus f of 1.5 times 0.5. And that's going to get me, the total area. Now, if I want to, go to my calculator and do this, I'm just going to kind of do it one trapezoid at a time. So my first trapezoid, I have the 1/2, and the f of 0 would be 0 to the 6th plus 0.5 to the 6th. And kind of look at what I'm typing in, times 0.5. Woo! There's one trapezoid. Yay. All right, let's do another one. So then I have 1/2, and I'm going to do 0.5 to the 6th plus 1 to the 6th. There's my second trapezoid. And then, last but not least, I'm going to do 1/2 times 0.1 to the 6th plus 1.5 to the 6th. And we got 0.5 again. So 0.5 is my kind of like the width of the trapezoid, kind of turned on its side. And we are looking at about 3.355. That is our final answer. It's pretty darn good, I think. And there we go. So once when you kind of get that function notation, then you can kind of, just let the delta math calculator, kind of take care of itself. And what is nice about the delta math solution is it does show you the function notation. It also shows you even what happens when you plug it into the function. Now I kind of just suggest once when you know what to plug in, I just suggest, letting the calculator kind of take care of itself. And there's also a nice graph, and you can kind of see how does the Riemann sum compare to the actual area and stuff like that too. So that is Riemann sum with equations with scale 35.